Okay, so welcome to our last session today. We start with the contributor talk by Alexander Wires. Tell us about central extensions, presentations, and Hochschild's and varieties of a difference term. Go ahead.
Okay, thank you very much for giving me the opportunity to present, and I hopefully sometime soon I'll be able to start coming to these conferences in person. Okay, so we should start. So what I'm looking at is the Hochschild-Serre sequence. So in the paper of Hochschild-Serre, there's as an application of spectral sequences. So really a kind of a pure development, a pure calculation in homological algebra. So something applied to a billion group chains. If you take the spectral sequence and apply it to a particular chain that's coming from a group theory, here M is a G module, so you have the following sequence here. So this is the Hochschild-Serre sequence, and in our case, we'll be interested in the dimension M equals 1. So in this case, the first three will be H1, and then these two will be H2, the second cohomology group. When the action is trivial, we recover the central extension. So these H2 groups, classified, characterized for groups, central extensions. And the H1 just gives us the Hom sets. And so we have this nice looking formula here. The Hochschild-Serre, together with something like the universal coefficients theorem, which looks at a billion extensions and then relates the cohomology with the homology on the Hom sets, then maybe you would use some facts like the billion group as a Z module. If Hom sets to the multiplicative group of the complex just gives you back your original algebra. So here we'd say this is self-dual. If your abelian groups are finite, then you have this very lovely, beautiful formula here where your abelian extensions, the Hom sets, and your tensors are related. So something like this helps you to break down very large nested formulas. Okay, so that's the homological calculus. You use those tools together, you get a lot of things. And of course, a lot of that development makes sense not just for abelian groups, i.e. Z modules, but for general R modules. And so if we wanted to think about something like spectral sequences in an algebraic setting, but in a more general universal algebraic setting, what would you think about or try to do? You might look at varieties with a difference term here. Since varieties with a difference term would be one way to answer the question of, suppose I wanted to have a class of algebras in which my abelian algebras with constants are basically R modules, but I still preserve all of the very nice commutative properties from group theory, as most of the properties as possible. But hopefully we'll see that varieties with a difference term are also maybe the answer of a place giving a general interpretation of spectral sequences for R modules coefficients. Okay, so that means in order to look at Hochschild-Serre in a general setting, we have to get down to thinking about what are cohomology for universal algebras. And we're going to take a slightly different tack. So I started on this project way back, I guess, I don't know how many years ago, 4 or 5 years ago. Maybe there was a AAA conference in Vienna, and I was looking through Jonathan Smith's book on Malta varieties. And there the approach, they have he has a little section on the Barback triple cohomology. But I think a slightly more down-to-earth, since we're just universal algebras, operations on sets, we can take a more down-to-earth approach and maybe get a little bit more So I'm looking at algebras of the following kind. So if I take my congruence and look at it as a subalgebra, and then look at a congruence of this way, I have the following algebra here, denoted in this way. In the case of groups, we can see that this just gives me this following semi-direct product, which tells me that if I want to think about cohomology, I want to think about starting with this kind of algebra and then
Alexander, can you hear me?
Yes.
Alexander, can you hear me?
I can hear you.
Yeah, look, we lost you in the main room. So can you just stop and we'll try and get the situation sorted out and I'll tell you when we're ready to go, okay?
Okay, so all right, let me reset my timer here so I don't go too long. All right, so yeah, so the task here is that the last few years I've worked on redoing cohomology for affine extensions for universal algebras and arbitrary varieties. So the problem here is we don't have normal subgroups, right? So congruence is not necessarily determined by a unique congruence block. And so what we need to do is consider algebras of the following kind, like here. In the case of groups, one can show that this is isomorphic to this kind of semi-direct product. So if H is the whole group, we just get the quotient and the kernel on the left of K is a billion. So my datum, the kernel of datum, the kernel of a extension is going to be the following structure, partial structure. So I have an algebra with a fixed ternary operation and then a congruence on this algebra. And then I have a sequence of partial operations. So I'm just looking at the first coordinates and diagonal elements here. I'll say this is affine if alpha is a billion in this algebra with a single operation, no other equations or equational theory supposed. And it happens to be affine on the blocks, alpha blocks. There is a notion of actions. So these are just pairings of the following form. So a lot of things from Q and then from A for each position. If you start composing actions, pairings of this kind, you can develop a model theory for the actions, i.e. given an actual equation in a signature, you can compose actions following the terms, and then look at those tuples for which everything makes sense. And then you can say the action satisfies the equation if the right hand, so this thing that's computed from the actions makes sense. If Q is an algebra, then these are mixed terms. So you have things in the pairings and in the signature of the algebra of Q. So we can say the action is compatible with an equational theory. That makes sense. Likewise, you can look at mappings from Q, powers of Q for the arity of the signature into this set. These will be our cocycles, and you can define what it means for cocycles to be compatible with an equational theory in a similar way by composing these cocycles with the action terms. That works out. So I'm going very quickly because I just want to highlight that the kind of situation we have. So you can put all of this together. So on the universe, on these sets, so on sets of this form, you can then put everything together, these partial operations, the action terms, and the cocycles with floating points defined over diagonal elements in the set. This defines a cohomology group in a classic way. Compatible two cocycles parametrizing extensions over the two co-boundaries. The co-boundaries satisfy every equation, so they're contained in every abelian group of two cocycles. We have extensions in this setting for arbitrary varieties. If the kernel is affine, then those algebras which realize the affine datum the semi-direct product. We can think of this as a semi-direct product since it's characterized by the retractions. We can group all of this together so we can look at the complete sublattice of varieties containing the datum on one side over here, and then look at two cocycles generated by any compatible cocycles. This defines a Galois connection in which we just look at one side, we look at the variety and then its extensions which in the variety which realize the datum. So the point here is that cohomology, in this setting, cohomology admits an additional parameter for the equational theory, the target that we're looking at. There's a notion of derivations and stabilizing automorphisms of extensions. We can even talk about principal stabilizing automorphisms. So in this setting, we can have a meaningful H1 group. In this case, central extensions just give us the Hom set for H1. There's a notion of trivial action, which unlike the group case, which is given by conjugation, trivial just means the identity, so i.e. recover a Z module, but here the trivial action works out to give module terms actually. So we kind of get what we wanted to get. So in varieties with a difference term, we can see that trivial actions, if we start with datum with trivial actions, central extensions, trivial actions characterize central extensions. So that means that if this action here is trivial in this meaning, then this group gives us exactly the central extension. So everything just specializes. Okay, so that's very quick, but the broad idea is that we recover a lot of the classic construction in a down to earth. So we're still just talking about operations on sets and clones and so forth. If we specialize to varieties with the difference term and central extensions, things simplify a little bit. So we have this classic construction from Friese Mackenzie's commutator book, chapter 7, the first theorem in that chapter. If we start with a binary operation, then we can take a set B and Q in the same signature and define something that looks like more classically like a semi-direct product without the action and the cocycle. So no rotation, but translation by the cocycle here. In a variety with a difference term, if alpha is a billion, then basically the theorem they didn't prove exactly this, but really this following holds. So this says that we can recover exactly central extensions, realizing datum in this way. So if you look at this algebra here, this will actually be affine, but even better, there's an idempotent element. The diagonal is a single element. The diagonal class is a single element and it's idempotent, which means that it's term affine. So the operations don't have constants. And so that's our notion of datum. We start with an algebra, which is term affine. Once we take our Maltsev term, or once we take our difference term and define the operation in the classic way. Everything simplifies in this case. So the action terms are folded into the module terms. The two cocycle equations simplified, but they're still there. So they're compositions of the cocycle into the modules. So we finally get to where the Hochschild-Serre sequence. So this is what we're looking at here. If we fix a particular central extension, so B here is this kind of algebra, this linear algebra, linearized algebra of A. Second projection realizes the extension. Then there is going to be a cocycle T, which represents that extension in the cohomology group. And then we can define our inflation maps and restriction maps in a classic way. The definitions from, let's say, Hom set to Hom set is given by precomposition. For cocycle on the left goes to cocycle on the right by the composition as well. This is the classic definition. Everything works out. So everything you need to check works. Restriction is a little bit different because the fact is we still don't necessarily have that B here appears as a subgroup, as a subalgebra. You know, it still doesn't make sense to identify the congruence by a special a congruence block. So what we have to do is we take our restriction and then have to subtract off something that represents an idempotent element. This is well defined. It's independent of any choice of Q, but it is still meaningful to have this subtracted element. The transgression is defined in the following way, the classic picture. It respects equational compatibility. This is new. It has to be checked. So equational theory and the cocycles match up, and it's bilinear. So it's a homomorphism in both coordinates. And so we can prove the Hochschild-Serre sequence in this general setting of varieties with a difference term. It's going, in general, it's exact in the Hom sets, the first three groups here, but it's not necessarily exact in the cohomology, second cohomology group here. That's an issue. And it turns out that it depends. I don't have an example right now. I'm cooking some up to realize the boundaries of things. But if A happens to have an idempotent element, then it's actually exact, and which corresponds to the classic case, and many other examples that are known we'll talk about. Okay, so the transgression is bilinear. So if we notice this map here, we fix an extension and the transgression. So T is fixed, and then we think of it as a function on the Hom set to second cohomology. So homomorphisms to cocycles. But if we think of it all together at once, we have the following theorem. So the transgression inputs the extension, inputs a cocycle, and maps to Hom sets of Hom set to cohomology. These are the abelian extensions. So Q modulo its commutators abelian. So these are just the abelian extensions realizing datum in the variety U. This is an exact sequence. The chain map given by evaluation. So B maps to evaluation by B on homomorphisms here. This is null homotopic. So that means that if evaluation is an isomorphism, right? If we have an inverse for evaluation, i.e., we'll just say that's a reflexive pair if this is an inverse. So we'll say that's reflexive. Then this, null homotopy with the inverse, this just gives us split exactness. And so we recover the direct product, second cohomology being the abelian extension times this kind of nested Hom set here. If Q is perfect, so if the commutator of Q is just everything, so it's neutral, then the left side, this is just trivial. And so that goes away and we just recover the classic formula. And so if B happens to be self-dual, then it breaks down and we have the following. So things simplify, right? So big nested formulas simplify. Finiteness here gives us the tensor products. Okay. Sometimes we can simplify. We have a notion of regular datum. So this just says that we're injective. So any homomorphisms from B to E, if lift are restrictions of homomorphisms when B is a subalgebra of anything, and we have separation, meaning that if we remember, B here is going to be datum, meaning that it's term affine. So this just says that if an element is not in a submodule, then there's going to be a homomorphism which kills the submodule, kills alpha, right? Kills the submodule, but still does not map the element to 0. So regular datum exists. This is the classic theorem about injective modules. Modules being embedded into ejective modules. But the unfortunate thing is that in general, we have to consider a larger variety. And that's a real sticking point. And so we have this following generalization of Scher's theorem where we can witness covers. That is, if our variety has an idempotent element, at least just one, really what it means is an idempotent element in an appropriate free algebra in the variety, then the transgression is an isomorphism. So this cover here, we call this a cover, meaning that it's injective. This tells us that the kernel is in the commutator. And surjectivity here relates to a mapping property, completing squares. And this is the classic situation of Schur, where projective representations of the quotient lift to regular representations of the parent of the extension. Consequently, this says that the cohomology for regular datum is always a reflexive pair though, right? So in general, because E is regular, that means the triple dual is isomorphic to the dual. And so because we're offset, so the thing isomorphic to a dual, that means this will be isomorphic to it's a double dual. So it's a reflexive pair. That's quite interesting. We always have that. All right. So we actually can also generalize Schur's theorem relating the second cohomology, so the Schur multiplier to a particular presentation, so relations modulo its commutator in the free algebra. So this is kind of a mess to look at. Again, the issue here is that we can't just restrict to special congruence blocks. So the way to think about this is maybe look to see how we derive Schur's classic results for groups. So if we have a finite group Q and a presentation for Q, then this thing here, we saw what this was before. So if we go back in this picture here, so H is just the whole group, right? So what ends up happening is that this just simplifies directly to this following group, but the presentation modular the commutator here, the relations modular the commutator is central in this free algebra modular the commutator. So it just simplifies in this case. So as a result, if we take this canonical homomorphism and push down, we just recover the intersection, the classic picture, the classic result. For any, if Q's finite, then Schur proves the theorem of Schur says that K, any central subgroup here, is intersecting the commutator is finite. So if we take this particular central extension that says this is finite, multiplicative group for complex numbers is regular for a billion groups, and so therefore the Hom sets, it's dual. We have this picture here. So we already said that this thing was equal to the push down, the image into the, so basically kind of like a submodule. So the point here being that sometimes, so what ends up happening is sometimes congruences below alpha when you push down correspond to special kinds of subalgebra. So if you have funny, interesting collections, interesting configurations of submodules downstairs, you can pull that up to interesting configurations of congruences upstairs below alpha. And so we get the classic result. So this is just the Schur multiplier. Okay, so varieties with a difference term are quite general. So I was talking about this result, I guess, last year at the Chinese Mathematical Society conference, and there's a lot of Lie algebra related research people there, and they told me that recently there's been a lot of work. So I went online and we might look at particular varieties with a difference term. And in fact, these are all just Maltzer varieties. So a billion groups expanded by linear and bilinear operations, linear being the module or the vector space. So just recently, algebras of Lotte, so Lie, Leibniz, Minelis, looking at dissociative algebras, Lie algebras, dendriform cohomology, and Hochschild-Sayre in these particular cases, dendriform in 19. So these are all really of the last year, this year, last year, and the year before, or Roeder-Baxter type algebras just this year, actually, this summer while waiting to give this talk. These have been posted on the archive. So for example, in each of these cases, they've independently redone the work, but what you can do is really just take our theorem here and just in each particular case, you just evaluate what this looks like. So in the case of dissociative algebras, if you happen to know what that is, then you would just look at what this particular algebra is in this particular variety. And here the Leibniz algebra gets the picture here. And so the theorem applied just to say, what is that? Gives us the results. And so this applies to new things that haven't been worked, maybe Zimbiel algebras I haven't seen. Hochschild-Serre for dissociative Rotor-Baxter algebras, right? I mean, you can just take the linear term, the bilinear term in the Rotor-Baxter equations and generalize that in the following, algebras of low-day type way. And recover, and the theorem applies in those cases as well. So in each setting, what you would do is, in each variety, you would just look at the generators of the commutator in that particular case. So for example, for dissociative algebras, the commutator generators is given by this picture. You identify what datum looks like, maybe the field in the case of Leibniz, the algebras, dissociative algebras, maybe ZP infinity if you're looking at a particular restricted class of finite abelian groups, or C, the multiplicative group of the complex numbers in the classic results are sure. And then utilize any self-duality or reflexivity. So you notice in this very general setting, we have Hom sets proliferate, yeah. And in general, they can't be gotten away with. But if you have any nice reflexivity or self-duality, these break down into the tensors and simplify. Okay, so there are a lot of questions. We're very, so our notion of regular datum can actually be tailored to any particular class of algebra you're interested in. So really, you just need datum that's regular enough for what you're looking at. And then you can complete squares, lift maps just for those restricted classes of algebras. This is interesting here because our cohomology admits, right, the U here, right? So the Galois connection that comes with our cohomology has this machinery to look at how the cohomologies appear as subgroups. So for example, in a variety with a weak difference term, solvable algebra form a subvariety, and so therefore the solvable algebras which realize datum appears as a subgroup of cohomology. This is a vast generalization of the fact that, like in groups, your abelian extensions correspond to symmetric 2 cocycles. Yeah, so this was.
Can you stop?
Okay. Okay, all right, good. Yeah, thank you very much. I guess that's it.
Okay, thank you. Maybe one quick question? Anyone? Yep.
Just something quick. It sounds like this is trying to generalize a sort of algebraic notion of cohomology theories to other algebraic varieties. Do you know if anybody has thought about, rather than assigning abelian groups or modules to topological spaces and doing cohomology with coefficients there, doing cohomology with coefficients in some variety? I guess that's what I thought this talk was going to be. So that might not be something you've thought about, but I'm curious if it's if it is.
So this is no, I haven't, and in general, that sounds like the way that one has approached generalizations of cohomology, where the target, the coefficients, are maybe you take the classic picture and then maybe look at like the triple cohomology or something like that, where the coefficients are special kinds of category, but one can define those things, but then what kind of theorems can you prove? So, and my incredibly limited, I'm not an expert or I have very little knowledge of this, but then you still need you still somehow to get theorems, results, tools, those coefficients are somehow derived structures from abelian groups. They're still witnessing an abelian phenomenon. And so in this case, the approach was to stay as close to the classic, maybe, I don't know, I've sometimes heard it called naive, to stay as close to the original papers of Schur and to develop a cohomology for arbitrary universal algebras. But still they have to have this abelian phenomenon. So there's still an affine operation on the congruence blocks.
Okay, thank you.